In 1905, a young physicist of 26 named Albert Einstein showed how measurements of time and space are affected by motion between an observer and what is being observed. To say that Einstein's theory of relativity revolutionized science is no exaggeration. Relativity connects space and time, matter and energy, electricity and magnetism, links that are crucial to our understanding of the physical universe. From relativity have come a host of remarkable predictions, all of which have been confirmed by experiment. For all their profundity, many of the conclusions of relativity can be reached with only the simplest of mathematics. Special relativity. All motion is relative. The speed of light in free space is the same for all observers. When such quantities as length, time interval, and mass are considered in elementary physics, no special point is made about how they are measured. Since a standard unit exists for each quantity, who makes a certain determination would not seem to matter. Everybody ought to get the same result. For instance, there is no question of principle involved in finding the length of an airplane when we are on board. All we have to do is put one end of a tape measure at the airplane's nose and look at the number on the tape at the airplane's tail. But what if the airplane is in flight and we are on the ground? It is not hard to determine the length of a distant object with a tape measure to establish a baseline, a surveyor's transit to measure angles, and a knowledge of trigonometry. When we measure the moving airplane from the ground, though, we find it to be shorter than it is to somebody in the airplane itself. To understand how this unexpected difference arises, we must analyze the process of measurement when motion is involved. The first step is to clarify what we mean by motion. When we say that something is moving, what we mean is that its position relative to something else is changing. A passenger moves relative to an airplane. The airplane moves relative to the Earth. The Earth moves relative to the Sun. The Sun moves relative to the galaxy of stars, the Milky Way, of which it is a member, and so on. In each case, a frame of reference is part of the description of the motion. To say that something is moving always implies a specific frame of reference. An inertial frame of reference is one in which Newton's first law of motion holds. In such a frame, an object at rest remains at rest, and an object in motion continues to move at constant velocity, constant speed and direction, if no force acts on it. Any frame of reference that moves at constant velocity relative to an inertial frame is itself an inertial frame. All inertial frames are equally valid. Suppose we see something changing its position with respect to us at constant velocity. Is it moving or are we moving? Suppose we are in a closed laboratory in which Newton's first law holds. Is the laboratory moving or is it at rest? These questions are meaningless because all constant velocity motion is relative. There is no universal frame of reference that can be used everywhere, no such thing as absolute motion. The theory of relativity deals with the consequences of the lack of a universal frame of reference. Special relativity, which is what Einstein published in 1905, treats relativity three problems that involve inertial frames of reference. General relativity, published by Einstein a decade later, describes the relationship between gravity and the geometrical structure of space and time. The special theory has had an enormous impact on much of physics, and we shall concentrate on it here. So in summary, motion depends on the frame of reference, meaning something is only moving relative to something else, and there is no such thing as absolute motion. Different observers can measure quantities like length differently when objects are moving. For example, a fast-moving airplane appears shorter to someone on the ground than to someone inside it. In inertial frames, where objects follow Newton's first law, all observers moving at constant velocity are equally valid, so no single frame is correct. This idea forms the basis of special relativity, which explains how measurements of space and time change with motion. Postulates of special relativity. The laws of physics are the same in all inertial frames of reference. This postulate follows from the absence of a universal frame of reference. If the laws of physics were different for different observers in relative motion, the observers could find from these differences which of them were stationary in space and which were moving. But such a distinction does not exist, and the principle of relativity expresses this fact. The second postulate is based on the results of many experiments. The speed of light in free space has the same value in all inertial frames of reference. This speed is 2.998 times 10 to the power of 8 meters per second to 4 significant figures. To appreciate how remarkable these postulates are, let us look at a hypothetical experiment, basically no different from actual ones that have been carried out in a number of ways. Suppose I turn on a searchlight just as you fly past in a spacecraft at a speed of 2 times 10 to the power of 8 meters per second. We both measure the speed of the light waves from the searchlight using identical instruments. From the ground, I find their speed to be 3 times 10 to the power of 8 meters per second, as usual. Common sense tells me that you ought to find a speed of 3 minus 2 times 10 to the power of 8 meters per second, or only 1 times 10 to the power of 8 meters per second for the same light waves. But you also find their speed to be 3 times 10 to the power of 8 meters per second, even though to me you seem to be moving parallel to the waves at 2 times 10 to the power of 8 meters per second.